Rao Bhim 9.3. We have already seen what a quadratic form is. A quadratic form consists of x, the variable, which is in our case an n-dimensional variable, so it is n cross 1. So this is its transpose 1 cross n, and A is a matrix which is n by n. Without loss of generality, we can assume that A is symmetric. We are always working with real quantities here. Our underlying field is R. In this connection, we have also seen that if I change the basis, in that case I get a different form for the same quadratic form, and that is given by the congruence transformation. If P is a non-singular matrix which represents a change of basis matrix, and I convert X to Px, in that case the same quadratic form now looks like X transpose P transpose, which is basically Px whole transpose times my old A times Px. So now it is again a quadratic form where this matrix plays the role of the matrix for the quadratic form, and we say that this matrix is, so the matrix A and this matrix P transpose AP are called congruent, and because the choice of the basis is basically arbitrary, so we can say that a matrix and any matrix congruent to it, that is any real symmetric matrix and any other real symmetric matrix congruent to it, basically represent the same quadratic form. Thus, suppose that this is the set of all real symmetric matrices, then the congruence operation, which is the congruence relation, which is an equivalence relation, will partition these into a number of blocks. So any two matrices here, every element here is a real symmetric matrix, in the same block are congruent to each other, and if I take one matrix here and another matrix in a different block, then they are not congruent. Then each of these blocks represent the same quadratic form. So the properties that we are interested in will be basically properties that are shared by all real symmetric matrices in the same block. Now, whenever we have such a situation, we generally want to look for one particular very nice simple representative for each such block. And I have already given you a similar analogy. When we work with fractions, like we say 2/4 and 3/6 and 50/100, these things are all same in terms of fractions. So we want to say that I want to get one particular reduced representation, and that reduced representation is half. So all these things can be reduced to half. So naturally we want to know if there is one particularly simple form that resides in every block, and such a thing is given by diagonal matrices. In other words, given any matrix, there is at least one diagonal matrix in the block of that matrix. So every such block contains at least one diagonal matrix. And this is the main statement of Theorem 9.3.1, which says that every real symmetric matrix is congruent to a diagonal matrix. Of course, Rao Bhim has not presented it in this way. It has presented it in a way so that you do not see the real interpretation of that, but this is equivalent to that. Now, proof of this is pretty straightforward. In fact, we have already learned the proof of this fact, and that is the following. Suppose A is a real symmetric matrix, then we know that A has a spectral decomposition. That is, it can be written as P transpose dP, where P is an orthogonal matrix. Now, any orthogonal matrix is also a non-singular matrix, so this thing is actually a congruence relationship. So it says that A and D are congruent, and of course The beauty of this lies in the fact that this D is a diagonal matrix. Its diagonal entries are precisely the eigenvalues of A. So, the spectral decomposition theorem immediately says that any real symmetric matrix is congruent to a diagonal matrix. In fact, because it is orthogonal, so the transpose is also its inverse. So, any real symmetric matrix is also similar to a diagonal matrix as well as congruent to a diagonal matrix. Now, in this chapter, we do not care about the similarity transform. We care only about the congruence operation. So, this is just a one-line proof of that fact. Now, if someone asks you to actually find such a D, that will be in general quite complicated if you want to use spectral decomposition. But remember, for this theorem, we really do not care about P being orthogonal. We are a lot less ambitious. It is enough to get P just a non-singular matrix. Now, since we are a lot less ambitious, so we can expect that we can work out some other way of obtaining such a diagonal matrix D and a non-singular matrix P. Of course, then the diagonal entries of D need not be the eigenvalues of A anymore. Now, the book gives you one particular algorithm by which you can actually construct such a non-singular matrix P as well as a diagonal matrix D using basically the idea of completing squares. But for theoretical purposes, all that we need is Theorem 9.3.1. We do not need a constructive algorithm to get this P and D. So, in this video, we shall be just satisfied with the spectral decomposition proof of this theorem and continue to the discussion after the algorithm. Now, coming back to our equivalence relation, which is given by the congruence relation, we have seen that in every block there is at least one diagonal matrix. Now, the question is the diagonal matrix unique? In the analogy that I gave, where you are writing 2 by 4 and 50 by 100, both of them are equivalent in the sense that they both represent the same fraction. We could reduce both of them to this thing 1 by 2 with the extra property that the numerator and denominator are relatively prime. Now, once you put that condition, then you can also say that this is unique. Now, can we make a similar statement here? So, is it that in every equivalence block there is exactly one such diagonal matrix? Now, the answer to that is obviously no, that cannot be true because of the very simple counterexample. Suppose we have a real symmetric matrix A which is equivalent to, that is congruent to this diagonal matrix where P is non-singular. All that I will do is I will just multiply P by 2 and that will still keep it non-singular. So I will put a 2 here and put the same 2 here. As a result, this will just get multiplied by 4. So you can see 4 minus 4 is also in the same block. So if 1 minus 1 is there, 4 minus 4 is also there, and you can do more exotic things like you can multiply this with 2 and this with 5. Simply do not use a single 2. You just multiply one particular column of P with something, some other column by something else, and still it will remain a non-singular matrix. So clearly, there are many diagonal matrices all residing in the same block that are equivalent. So the next question is, can I further reduce it? Can we say that there are certain properties that are invariant? If there are a number of diagonal matrices all residing in the same block that is congruent to each other, then they must share certain property. And one such very important property is given by Sylvester's law of inertia, which says that if I have two diagonal matrices, I should better write diagonal, both of them are diagonal matrices, and I say that they're equivalent, meaning that they are congruent to each other, then the number of positive diagonal entries must match. The number of positive entries in diagonal of D1 must be same as number of positive entries there. Similarly, number of negative entries must match and number of zero entries must match. So let's take an example first. Thus, it is quite possible that this D1 and this D2 are actually congruent. That is, you can find some non-singular matrix such that D1 and D2 are related like this. D2 is some P transpose D1, dP, where P is a non-singular matrix. Just observe that number of positive entries here is 2. These two are positive entries. Number of positive entries here is also 2. The values are completely different. Their positions may be completely different. That's not a problem at all. You can control those values and the positions by just switching P. But the number of positive entries, that you can never change by choosing P suitably. Similarly, number of negative entries here happens to be 1. Here also the number of negative entry is 1. Number of zero entry is 1 and number of zero entry here is also 1. So the exact values do not matter. Their position do not matter. All that matters is the number of positive, number of negative and number of zero. Now actually we can make a stronger statement. Though this is Sylvester's law of inertia, you can actually also prove this thing, which is actually the easier of the two. So this is an if and only if relationship. So if I give you any two not real, just real symmetric, but two diagonal matrices, real diagonal matrices, just by looking at it, you can say whether they are congruent to each other or not. This side is the trivial part. I can leave that as an exercise. This is the non-trivial part, which is called Sylvester's law of inertia. Now, Sylvester's law of inertia theoretically is an interesting result, but it is not really considered one of the most important theorems in linear algebra. In fact, many books do not even mention that. Now, we are going to prove it. The proof is pretty straightforward, but before that, let me make two comments. Comment number one, this guy Sylvester, you may not have heard his name. He is a very colorful character. He used to be a math professor in the United States of America. In fact, he was a founder in some math department, was highly regarded in that country. Then quite unaccountably, he left his job and came to England, became a lawyer. Out of all professions, he became a lawyer. And there he met another fellow lawyer by the name of Cayley, whom he got interested in mathematics. And during their spare time, Sylvester and Cayley would solve various puzzles and math problems. And this Cayley is the same Cayley as Cayley-Hamilton theorem. And they got various interesting results. There is one contribution of Sylvester that we use all the time without knowing. Whenever we use the term matrix, we are actually using a contribution of Sylvester, because Sylvester was the first mathematician to use the word matrix in the context that we know it today. So that is point number one. Now the second comment that I want to make is this fact, this invariance of the number of positive entries, number of negative entries, that has an interesting interpretation. So I will give that interpretation first and go to the proof later. When we define norm of an n-dimensional vector, we use this formula. So I am using just what is called the Euclidean norm. Now you can think of it in the following way. You were writing x1 ... xn, then you were writing 1 1 1, so you were writing a quadratic form, basically x1 ... up to xn. So you can think of it as a quadratic form. Since you have only the square terms, you have only the diagonals, all the off diagonals are 0 because you do not have any xi, xj term. So all of them are 1. Now if you change the basis, you can represent the same thing using some other matrix, and that matrix will be congruent to the identity matrix, and that is of this form. You started with I, you change the basis, as a result this x now gets converted to px, so it is x transpose p transpose. So this is, because multiplication by identity doesn't change anything, is simply x transpose p transpose px. And that is why these matrices become very important. They are, we are going to learn pretty soon, they are called positive definite matrices, and they give you the general form of norm in case of Euclidean product, in case of Euclidean norm when you are choosing some other basis. Now there are situations, and that is why Sylvester's law of inertia comes into picture, where you do not want to keep all these things equal to 1, but you want to inject certain minus 1s here and there. That is also one form of norm, but this norm is not what we call norm, in the sense, if we allow negative, suppose we put a negative here, in that case this will mean from 1 to n minus 1, you are adding all those things, then finally subtracting xn square. So obviously this can become negative. For example, if you take all these things 0, but xn equal to 1, then this value will be minus 1. That is also one type of norm. And if you change the basis, in that case, you will always find that you will have exactly n minus 1 of them positive and exactly 1 of them negative. The positive values may change, their positions may change, the negative value may change, position may change, but the fact that there is exactly one negative will never change. And this becomes very important because this obviously becomes a property of the underlying, of the norm itself, and not a property of the particular basis that is chosen. In fact, we have already seen this notation, Rn, and when you do this, you are also allowing a minus 1. You typically call it Rpq, which basically means that there are p1s and q minus 1s. We are not specifying the position because the position and the positive and the negative entries might change depending on what basis you are choosing. For instance, if I am working with R31, it is same as working with R4, except that my norm will be given by 1, 1, 1, minus 1. That is, if I give you any vector which is x1 to x4, in that case its norm will be defined by summation xi square 1 to 3 minus x4 square. So this will be called the R31 space. Now this particular space is of great importance because it is also called the Minkowski space. Minkowski is the name of Albert Einstein's professor. And when we say that we are working with space-time and time is a fourth dimension, we really are not working in R4. We are actually working in 3-1. These 3 denotes XYZ in space, and this 1 denotes time. Now, why exactly we need minus 1? That is an interesting story and not very difficult to understand. However, in this video, we shall not go into that. I just wanted to mention that this 3 and 1 is used in something very real. And the fact that I can write 3 and 1 without having to write down what particular basis I am using, that comes from Sylvester's law of inertia. So this 3 and this 1 are properties of the space and the norm, and not going to change based on what particular basis you choose. Okay, so this video is getting a bit long, so I think it will be a good idea to postpone the proof of Sylvester's law of inertia to the next video.